Well, I'm presenting the data, but this data and all the work we have been doing in the Meastart Basin, it's in collaboration with other researchers like Enrique Gomez, Ana Travé, that is today as a chairman, with Montad. Also Ramon Salas, Jaume Vergés, Mercè Corbella, some PhD students like Yao. Anyway, there are a lot of people contributing to this issue. Later on, I will say something about the industry relevance. There's something that the previous speakers have mentioned, but it's well known that the fault control dolomites have been of increasing interest during the last decades. Now this is led. Yeah.
Can you please make it on a slideshow?
Okay.
So that it will be more clear.
Okay. So the interest is now still high, but
it's still there. Can you have a slideshow, a full slideshow? Because we see two screens.
Okay.
Yeah.
Now?
Now it's disappear.
Okay, sorry. I'm gonna. I don't know. Sorry.
If you share it again, maybe.
No.
No, it's okay. Perfect.
Okay.
Yeah. Go ahead.
Okay, so I was talking about the importance, the industry relevance of these fault control dolomites. As you know, numerous equivalent hydrocarbon reservoirs in Middle East, Canada, and some other parts of the world. What's controlling the extent of the dolomite bodies related to the fault, which is the seismic thing that we can see, is not well constrained. Later on, the distribution of the genetic heterogeneity, which is closely associated with reservoir quality variability, is still poorly or not completely understood. I'm showing some pictures from the Meastart Basin. This is an example of Serra Esparraguera, where we see a late Jurassic succession with nearly 200 meters of dolostone, 100 meters that has been replaced completely or nearly completely replaced by dolomite. This is a macro scale heterogeneity that can be seen in a seismic profile. And later on, we have some what we call meso scale heterogeneity. When we go to the succession, this is another example. It's not in the same place. This is in the Benicassin area, and in here we have limestone beds and dolostones that have been replacing these limestones. We have 20 meters of dolostone, and some other are less thick. So we have again heterogeneity that is associated with this dolomitization process. And later on, we have a micro scale heterogeneity, what we call a micro scale heterogeneity, and this is three images of the same bed. One part of the bed has not been replaced. Another part of the bed has been replaced, and we have nearly no porosity, or a small porosity here in the bottom right associated with fracturing. And later on, we have an example of dolomite with a very nice intercrystalline porosity. Anyway, showing in here that we have a microscale heterogeneity that is very important for reservoir quality in the subsurface. So what I'm going to show today about the dolomites cropping in the Benicassin area. This is Meastart Basin. I will try to show the relation between the dolomite bodies and the fault system. I will try to show also the positional, diagenetic, and structural controls on the dolomite distribution. I will show some data about the timing, the origin, and the composition of the fluids. And also the distribution and variability of the genetic alteration, and thus porosity and permeability. So I will try to show a piece of everything for you to see what we have been doing in the area. Well, this is a map of the Meastart Basin. The Meastart Basin is an extensional basin developed during the late Jurassic, early Cretaceous reef cycle of the Iberian reef system. Here we have the Iberian Peninsula. This is France to the north. This is Portugal to the west. This is the Iberian chain, and the study area, the Meastart Basin is in here. What we have in the large map is a paleogeographic map in the late Jurassic, early Cretaceous reef cycle, showing the thickness of the succession of this age. As you may see, that there are very gray, dark gray colors here and here, and this gray color is representing a succession of more than 1,000 meters of late Jurassic, early Cretaceous sediments. Later on, there are some other light gray color, which is the succession is between 100 and more than 1,000. And later on, we have in the borders to the north and to the south, the seam reef thickness is below 100 meters. And we are located here in this Benicassin or Pesa area, which is still limited by two regional faults. This area had two deformation events post-dating the rifting, the Mesozoic rifting, one during the Alpine contraction and inversion, and later on the second one during the Neogen extension, which make the Western Mediterranean basin to open, and this is why now we have this coastal line in here close to the study area. This is the map of the area. Here in the bottom right, here we have a small piece of the Mediterranean Sea. So the coastal line is in here, and here we show the early Cretaceous sediments in this late color, and in brown or in orange color the Dolomite in the area. So we have a succession of early Cretaceous, as told you before, that more 2,000 meters. The Dolomitization is restricted to upper Aptian sediments. This is the Benasal formation. So this orange, green color is Benasal formation, and it's important to say that this formation has been replaced by Ferro and Dolomites. We have also this Mississippi Valley type mineralization that I will show you later on. This is a biostratigraphic, chronostratigraphic, and sequence stratigraphy panel of the area. So here on the right, the lithostratigraphy in this color, green color. We have the Benasal formation, and the Benasal formation we distinguish three main transgressive regressive sequences. One in here, the second in here, and the third finer than the other. But all three have been characterized through the area. We have a control on the age of the sediments by orbitolinids and ammonites. And the age by the end is this is a null now. Middle Aptian is not so we have late Aptian, Gargassian to Clonsasian, and we think we arrive to early Albian. This is something that we still have to constrain. Anyway, this succession and the components is age equivalent to the producing hydrocarbon reservoirs like Casablanca field in the Mediterranean, Sakum field, Shoaiba formation. So this area could be an analog for carbonate reservoir quality characterization elsewhere in these areas. This is a view on the top side of the range, with very well bedded succession. Here we have the bottom in the left, and the top on the right. You may say all of this is limestone, except this brown color on top, which is the dolostone. We will see later on these dolostones. And in here, what we have is exposed carbonate succession, mostly in the hanging wall position. We have a shallow water basin to outer iron environments. Here you have some of them. We have basinal marls. We have orbitolina waxstone packstones, very typical of early Cretaceous. We have also Rudis flowstones, typical of the Aptian sediments. We have also facies with corals, and also more grainy facies with palloids. So these are the typical Urgonian facies dominated by corals, orbitolinids, rudists, and algae. This is the correlation panel through the study area. In here we have the three sequences 1, sequences 2, and sequences 3 with different colors through the area. In here in red vertical lines we have the faults, Benicassim fault. Here we have another important fault, the Campanian fault, and as you see between faults, the succession is reducing. So these faults were active during the rifting, were active during the deposition of the sediments, resulting in here with a very thick succession, 1,700, 1,300 in this block, and in this fault block only 700 meters, which is very reduced compared to the other ones. You may see here we have a lot of facies. I'm not going to be very specific about this, but there are a lot of facies that we have been checking through the area and make this correlation that has been published recently by Yao in cementology. Here again we go with the map, and I'm going to show now more specific distribution and geometry data of the Dolomite. So these in red color are the important faults, regional faults. These are the Dolomite then is controlled by these seam reef Mesozoic faults. So we have a lot of Dolomite here in orange color, here in the cross-cutting between these faults, but we have also here in this area of the fault, and in here also we have some of them, but mostly is in here in the handing wall of the Benicassim and the Campello fault. I'm gonna have to say that due to the alpine and the Neogen extension, the bodies, the Dolomite bodies, are offset, have an offset, and some of them are covered by this white color, which is the quaternary deposits. So nowadays it's difficult to see, to follow all the bodies from the fault to the away from the fault, but I will show you some of the data that can be checked. As told you, in close association also with this regional fault, we have Mississippi Valley type mineralization, lead mineral. So these fault zones, these regional faults, are the source for the heat, and also for the fluids, not only for magnesium-rich fluids, but also for mineralization fluids. And the succession is in lateral contact with basement rocks and red beds, which is important. We will talk later on about this. So in here, through this Benicassim fault, we are in contact with Permotrias and red beds, Permotriasic rocks, Jurassic rocks, and also the basement more to the west. So I'm going to show some of the Dolomite bodies in here, more in these field images. These are dolostone patches bonded by fault. Here, these red lines are the faults, and we have some patches of dolostones. This is here in the Ferradura fault block. This also it's a contact, which is a kind of contact between a fault-related dolostone body and some more strata-bound dolostone, making this Christmas tree contact between the dolostone and the limestone. This is here typical from the Rocco del Moro site. And this other also in rhacodal morosite showing the stratabound dolostone. In here we have the gray color is the limestone, and this brown color with more vegetation is the dolostone. As you may see, it's following more or less the stratigraphy, and also we have some beds, limestone beds here between the dolostones that have been replaced. So following this dolomite distribution and geometry, this is a rhacodal morosite that I was showing, the dolostone in brown color, the limestone in gray color. More or less is a stratabound or substratabound. So there is an excellent lateral exposure, and a seismic scale. Here we have not the scale, but between the right and the left side of the image, maybe there are 3 or 4 kilometers. This is a close view of the area. Here we have the 150 thick meters of the dolostone body. And also in this area, we can see that this limestone floating between the dolostone. So it seems that there is a depositional control, or may indicate that we have a depositional control on dolomitization. The dolomite itself, this is a close view of the dolomitization front. So they are sharp. Most of them are sharp and wavy. Here you have the close view, the diagenetic front, more or less sharp and wavy, and here again this wavy and sharp contact between the limestone and the dolostone. The dolostone preserve the sedimentary structures and fabric, so it's fabric preserving, and this can be seen in the field. As Alessandro was saying, it's very easy to see this in the field, and I think the field data is always very important to figure out how the dolomitization occurs. And in here in this image we can see the lamination, original lamination of the dolostone, sorry, of the limestone. Here have some close laminated faces completely dolomitized nowadays. And in here we see that this is also a completely dolomitized rock, but what we see in the surface are the orbitolina, so perfectly seen in the surface of the rock. Again, it's very important to check well the outcrop, because there are a lot of things to see in the field. So talking about the undolomitized limestone beds that we find in the succession, this is a close view of the rhacodal moro, the same outcrop we were checking before. Here we have the succession. In orange color we have the dolomitized part. Most of the limestone that had been replaced correspond to grain-dominated facies, mostly Paxton to greystones, although it's important to say that there are also mud-dominated facies replaced, but the dominant replacement took place in Paxtons and grainstones. This is a very nice view of one of the outcrops. In here we have the dolostones in the lower part, and the limestone in the upper part. And you may see there is a very sharp contact, undulating contact. And with this image, I would like to show how stylolites are controlling dolomitization. If we go to a close view in here, we can see this stylolite system and how the dolostone stops in this stylolite system. This is layer parallel stylolites that cross or intersect with others, forming a network. Here we have a closer view, and in here we have a stylolite and another one in here. The dolostone is in brown color, and the limestone in the upper part in more late gray color. So the fluid was coming in here and was coming in here, and there was a stopping in here. If we still have more fluid circulating, probably it will overcome the stylolite and will stop later on in the next stylolite. So we think that these kind of stilolites networks have been controlling at least in part, the dolomitization. It's important to say that these stilolite networks are abundant in the mud-dominated phases. Mud-dominated phases are usually highly stilolitized. These anastomosing stilolite networks prevent the dolomitization of the complete dolomitization of the limestone. So, according to the data we have, these are effective seal units, and they allow the fluid to go more laterally than vertically in the succession. If we go again to the limestone that has been now dolomitized, I would like to show you some porosity permeability data. These are some of the phases: spicle maxstone wakestone, orbitolinate wakestone packstone, skeletal palloidal grainstone, completely cemented by calcite and dolomite, and oid grainstones completely cemented by calcite. So in here we have a plot with the permeability in vertical and porosity in horizontal, with different phases in blue, red, and green color. All of these again is limestone, and as you see, it's really very low porosity, between 0.5 and 1%, which is really nothing, and very low permeability. Really nothing again. So it seems that there is a phases control on dolomite distribution in here. We recognize a strong impact of early calcite cementation and in the diagenesis in the dolomitization, and these units that has been not replaced because of these early diagenetic processes are vertical barriers for dolomitization, which means that they enhance lateral fluid flow and make these dolomite bodies to be more strata-bound or stratified. This is the burial history of the area. In the right side, we have the succession from the basement, Carboniferous basement, the Triassic red beds, Jurassic, and all the Cretaceous. This green color, the light green color, is the Venasal Formation, which is the Venasal Formation we have been studying. In the Venasal Formation in here, we have three sequences: sequence 1, sequence 2, and sequence 3. And in here we are gonna show the constraint on the timing of dolomitization. We have seen from the field data that stilolites form before dolomitization, because stilolites are barriers for the magnesium-rich fluid. So we assume that this stilolitization took place before dolomitization and start around 500. Let's say something that is in the literature. It could be between 5 and 800. So we constrain at 500 to wide the time of dolomitization. And later on, we have another point, important point in the history, which is the MVT, the Mississippi Valley type deposits, were dated by Fidel Grandia. This is in the literature, and it was dated as 62.6 million years, which is the maximum age for dolomitization, because the mineralization is hosted by the dolostone. So the time of dolomitization is here between 100 and 62.6 million years, and around 500 and 750 meters. So we have done, and this is data that we have still not published. We have done some uranium lead datation, and dolomite was formed between 100 and 90 million years, which means that the constraint we were assuming for the area sometime before was fine. This is the paragenetic sequence that we came out after studying the limestones and the dolostones, and in here there are a lot of diagenetic phases and events. We have a time of shario-boreal eugenetic diagenesis. Later on, we have the intermediate boreal mesogenetic, and in here the dolomitization took place. And later on, we have the uplift, and as I tell you, we have the alpine orogenesis. Here in the right column, we have the effect of the porosity permeability on the rock. Here, the most important data we can say from here is that we have early calcite cementation. As told you before, there are some evidence that this early calcite cementation has been preventing the dolomitization of the complete succession. Later on, we have the formation of stylolates that are formed before dolomitization. Later on, we have the boreal dolomitization. This is not a boreal as we saw in the boreal core. It's not really a deep boreal, but below 1,000 meters. So here we have the boreal dolomitization, and we have also over dolomitization by dolomite cement at the end of the process. Later on, we have some boreal carbonate cements, and also the ore deposit. And during the uplift, we have the calcitization. I mean the calcitization of the dolomite, and also cementation by meteoric calcite, which is basically destroying most of the reservoir quality of the rock. So there are rocks that are in the surface now, but most of them are cemented by meteoric calcite. So this is the dolomitization process with some images. First, we have a pre-replacement. We call a pre-replacement, which is the dolomite cementation. Later on, we have the replacement process. We replace the limestone for a dolomite. And later on, we have recrystallization, which means that we make the dolomite crystals bigger. And this recrystallization generates some porosity, as you may see in the image. So starting with the dolomite, the precipitation of Dolomite 1, called Dolomite 1, which is the first dolomite cement to precipitate, represents the early stage of replacement. It feels intergranular and moldy porosity in grainstone, muddling packstones and packstones, but also in some other phases. It portrays the early calcite cement, and here, and then mechanical compaction, and the occurrence of matrix of some micrite may facilitate the dolomitization of packstones. The second stage is the replacement itself, the replacement dolomite. The formation of replacement dolomite 1 represent more or less 60% of the dolomite in the area. It's a tight planar to non-planar crystal mosaic. Is basically preserving the fabric. As you may see here, this is a completely dolomitized sample, and here we have ghost of the pelloids, which indicate that this rock was a palloidal grainstone, completely dolomitized. We have scattered intercrystalline and baggy porosity here with very light blue color, not too much porosity in this replacement dolomite 1, and these images are showing that there is a preferential replacement of grain-dominated phases, packstones and grainstones. And later on, we have the recrystallization of the dolomite. This involves the reorganization of the pore system and an increase in porosity. This is associated with higher permeable zones. This is fractures and connected porosity, fracture corridors, etc. It generates planar to non-planar crystal mosaics, and involves an increase in crystal size, dealing with a sucrosic fabric of the dolostone. This is an electron microscope image of the dolomite. In here we see a transition between the replacement dolomite 1 mosaic, fine crystals, as you may see here, fine crystals, fine crystals. There are some porosity, and the porosity it's open. It's not filled with calcite. And if we go to the right and top, we get bigger dolomite crystals. This is the replacid dolomite to mosaic coarser crystals. As you may say, this porosity, the porosity in this replacid dolomite to mosaic is filled with calcite, suggesting that the generation of the replacid dolomite 2 is reorganizing the pore system. The pore system is more open to fluids, and it's more open to cementation by calcite. What in the replacid dolomite mosaic is not seen. So by the end, the porosity permeability characteristics is enhanced in higher degree of recrystallization. So we have more porosity here originally, not now, because this calcite is in fact meteoric, so it's from the late stage. And if we go close to one of these big crystals of replacid dolomite 1, replacid dolomite 2, what we have is a core of the replacid dolomite 1 in here, and a border of the replacid dolomite 2 and calcite cement filling the crystal edge porosity. After the dolomitization, what we have is a leaching of the remaining skeletal grains. In the left image, we can see a dolomite view, and in here we had a skeletal component that were dissolved. And after dissolution, we have a cementation by calcite. Here we can distinguish that here the fragment was dissolved, and also there were a crack from this component probably to another component, which is typical, something typical seen in coarse grain or radstones, grainstones, and this kind of phases in carbonate. So this leaching of the remaining skeletal grains created abundant moldic and baggy porosity. To the right, you see some images in electron microscope. In the center, something similar to the previous one. We have this dissolution. Later on, we have a cementation by dolomite, which is this over the dolomitization that we were describing. And later on, we have calcite. In this case, probably this is meteoric calcite from the late stage. And in the right one, we have an open crack, still open after dolomitization and over dolomitization. So this porosity generation by dissolution, leaching of skeletals is common in secondary dolomite. It has been described in other examples. It's also typically reported in full associated dolomites. This has been also described by Wilson 2007 and Sharp 2010. And the best reservoir is found in replacid dolomite with intercrystalline and biomoldy porosity, more than 20%. And this is also enhanced by late fracturing. After the leaching of the skeletals, we have the cementation by planar dolomite, and we can say from these images that the fluid flow was following these cracks between bioclasts, cracks that were connecting bioclasts, and this is also enhancing porosity in the rock. Talking about the intercrystalline porosity, this is a classification in the center by Warren 2000 of the pores, taking into account the porosity and the permeability. And then in here we have, with low porosity, interboundary pores. These interboundary pores is what we have in the close view of a confocal large scanning microscope image. So we have crystals, dolomite crystals, and the porosity is along the edges of these crystals. And we have better connectivity, not connectivity, but better, bigger pores, which Warren called tetrahedral pores in this image. Again, a confocal laser scanning microscope image, very large porosity. All the rock in gray color is dolomite, and the porosity has been filled with resin with this color. And later on, we have with bigger, better porosity and permeability, the polyhedral pores, where we have these very nice planar E to planar S dolomite crystals, and in red color calcite that is filling now the porosity, but this is a late process during the uplift, but showing a very nice porosity at time of dolomitization. So if we go back to the dolomitization process, and here we have carbon-oxygen isotopy, typical for this kind of dolomite. Alessandro was showing similar themes. Carbon on vertical, oxygen in horizontal. Here we have the early Cretaceous marine carbonates. In here we have the signature of the matrix and the signature of the rudist shell, which is more or less fitting with the early Cretaceous marine carbonates. Later on, with less oxygen, with the plated oxygen, we have the dolomite cement 1, which is the first stage of dolomitization. Later on, we have the replacement process in orange color with the dolomite, replacive dolomite 1, and with more the plated oxygen isotopes is the replacive dolomite 2 in yellow color. So we can say that this range, this evolution, this represent variation in the temperature of the dolomitation fluid, is consistent with the formation of a more stable replacive dolomite 2 with by the recrystallization of the replacive dolomite 1. And it's important to say that more negative oxygen 18 values, which represent higher temperatures, occurs in the proximity of faults. Something more about the dolomitation fluids. This is a strontium isotopy plot, and here we have the strontium isotopy. In the horizontal, we have the oxygen isotopy. In here, we have the lower Cretaceous sea water. Again, the strontium isotopy of rudist shells and host rock matrix micrite is fitting well with this signature. But as you may see, if we move to more radiogenic signature, we get the dolomite cement in red squares here, or in orange color, the replacive dolomite 1, and in yellow color, the replacive dolomite 2. So this signature is consistent with upper Cretaceous sea water. So probably the dolomitization fluid was associated with upper Cretaceous sea water, and also we have a signature in burial calcite and saddle dolomites, which are these black points, still more radiogenic, probably indicating that the fluid circulated through siliciclastic, probably the Permian and Triassic red beds that are in lateral contact with by faults with succession. We have no really a nice data set in fluid inclusions, but we have evidence of high temperature fluid. I have been listing here some of these evidence. Sharp and irregular dolomitation fronts were described to be high temperature, typical of high temperature fluids. Dolomite non-planar texture. This is more controversy now because it's not completely true in all the times. We have also saddle dolomite. I have not been talking about saddle dolomite cementation. There are some, but it's not very, very important in the area. But we have some saddle dolomite, which means that we are above 80 degrees Celsius, which is indicating also high temperature fluids. We have a progressive depletion in oxygen isotope from dolomite cement to replacive dolomite 1 to replacive dolomite 2, which is also indicating some high temperature fluids. We have this typical dull red color under cathode of the dolomite, which is also indicating high temperature, and later on the associated mineralization, which is indicating probably not a high temperature by hydrothermal fluids. I told you that we have no nice data set and fluid inclusions. We have to work on this, but we have some of them, and these fluid inclusions for recrystallized dolomite and saddle dolomite are indicating temperatures between 100 and 160. We think about the burial depth we were calculating for the dolomitization was below 1000, which means that this temperature has to be reached by the host rock through hydrothermal fluids. After all the process of dolomitization, we have uplift, as have been shown by the or represented in the sequence, paragenetic sequence. And here we have a meteoric calcite cementation, which is destroying most of the reservoir quality of the rock. In the left-hand image, we have a replaced dolomite 1 plus replaced dolomite 2 crystal mosaic. This is red stain, very light red color, but all this is calcite. Calcite completely destroyed this porosity. We have a cathode color. We have the red color typical of the dolomite. We have the dolomite cement 2, which is the over dolomitization, and still we have a pore that has been filled with this meteoric calcite, typical meteoric calcite with a black cathode signature. And in the right bottom image, we have the scanning electron microscope with this over dolomitization, dolomite cement cementing the dolomite crystals, the replaced dolomite crystals, and later on the calcite, meteoric calcite filling nearly all the porosity. So the dolomites, the meteoric calcite is associated with a calcitization of the dolomite, which is the dolomite. It occurs via meteoric fluids that flow through the connected pore system, and there is a pervasive alteration of dolomite in fault areas where the meteoric water infiltration were more active, and in this area what we have is the dolomite completely de-dolomitized or calcitized. We have a lot of iron oxide around, and we have a very dark orange, brown, red color dolomite show indicating that the dolomite itself is partially de-dolomitized or calcitized. So this is the complete carbon and oxygen isotopy plot. The upper part is the dolomitization process that we were showing before, from the host rock to dolomite cement, replaced dolomite cement, replaced dolomite 1 and replaced dolomite 2, which is the recrystallized dolomite. This is the trend, and from here we go to a meteoric alteration due to uplift. And here we have the calcitized dolomite and also meteoric calcite cement. This is a dolomite porosity permeability plot, also showing the limestone. The limestone are square symbols. The dolomite are in round. Open symbols indicate perpendicular to basin data, and as you may see, this is the data we were showing before, limestones with very low porosity and permeability, and we see an increase in the dolomite porosity and permeability with respect to dolomite. So, with respect to limestone. So dolomitization enhanced porosity permeability of the host rock. currently only maximum 8%, and this is due to the meteorical site cementation associated with uplift, something that we were showing before. And we have higher permeability values perpendicular in those samples measured perpendicular to bedding due to the recurrence of vertical fractures. This occurs in thin dolomite bodies. Anyway, these are the trends. In blue, the limestones. Sorry, this is changed. The blue is the limestone, and in red the dolstones, and this is the trend of the increasing porosity. So I'm going to be finishing. I don't know if I'm totally well. It's I think we have time, but I'm gonna end with a conceptual model. In the upper part, we have a cross section of the basin from the south to the north. This is the Meastart Basin. We have an area of in Vistabella. We have very reduced succession of the early Cretaceous, and in here we have the Peña-Logolosa subbasin, and in here to the right, there's the Salsadella subbasin, where the thickness is bigger here and in here, both margins of the basin controlled by faults. So assuming this configuration of the basin, we came out with this conceptual model where we have these faults that were inherited from the rifting that had been reactivated during the late Cretaceous. In the late Cretaceous, we have seawater circulating downwards through this fault system and the succession. Once in the subsurface, the water was heated and enriched in iron. So here we came through circulation through this fault system of the basement faults. With basement fluids, and later on we have also formation fluids that are probably participating in the Dolomitization. Anyway, we have these magnesium-rich fluids with iron, high temperature, probably hydrothermal for the setting we have, and once they reach a seal. I mean, not talking about the seal, but we have some formation on top of the Benasal formation, which is considered a seal because it's made of clay. This is the Kucha formation. Once the fluids reach this part of the setting, the fluid cannot go and penetrate the Benasal formation laterally to form these strata-bound bodies that we can see in the area. This configuration of this conceptual model is something similar to what has been described in Canada. This is a model from the British Columbia by Davis and Smith, 2006. And in here, what we have is something similar that we are showing. We have in blue color, we have the limestone, the platform to seawards go to fine grain sediments. We have a green color on top that is the seal. Once we generate the fractures on the platform and the fluids reach magnesium fluids circulate through the faults upwards. At some point reach the green color, which is the seal, and the fluid goes laterally to form these strata-bound bodies, and along the faults these fault-related bodies. So we have these two bodies, the fault-related and the strata-bound, generating a Christmas tree geometry. And after this Dolomitization, in pink color. After Dolomitization, we have the mineralization fluids generating the Mississippi Valley type deposits in the area. This is from British Columbia. The image we have on the top side is the area we were studying, where we have these strata-bound dolomites that maybe it's something equivalent to these parts in here. And we also have in the area a mineral deposit. It's not really important from the point of view of the economic point of view, but it's something that is important to mention. Anyway, I will be concluding with some important issues. Dolomitization of the Benasal formation took place in a post-reef regime. This is late Cretaceous. It's a shallow burial, so it's less than 1 kilometer. Temperatures are assumed to be above 80 degrees. We assume for following the burial curve that is hydrothermal dolomitization. Hot fluids were most probably derived from seawater, from late Cretaceous seawater that circulated through the Paleozoic basement or the Permo-Triassic red beds, get the iron, and later were channelized upwards along basement faults, and laterally through most permeable bed of the Benasal formation to form these strata-bound bodies. The macro-scale fluid flow at basin scale is probably associated with a late Cretaceous regional thermal event that have been described in the area and caused dolomitization and Mississippi Valley Tap ore deposits at variable stratigraphic levels to the Meastart Basin. We have been describing in here the Benasal formation case study, but we have dolomitization of some other formations, units through the basin. So it depends on the fault system and the place in the basin where you are looking. So depending on that, you dolomitize one stratigraphic level or another, and this can be seen through the Diagenesis Meastart Basin examples. Some other conclusion as major controls on dolomitization. We have seen examples of controls by faults. These are regional faults, big faults that are basement faults that are feeding points, and also it's important and controlled by the fracture system. Although I have not been talking too much about this fracture system. Also, we check this early diagenetic calcite and dolomite cementation, preventing the complete dolomitization of the succession. Also, the importance of the chemical compaction, stylolite facies or stylolitized facies are not replaced or used to be not replaced, which is somehow controlling also the dolomitization. Also, the hot rock fabric, grain-dominated facies preferentially replaced, grainstones, backstones. And it's important to say that the matrix, the replacement of the matrix, the replacement of the micrite probably enhance the complete dolomitization of these backstones. And something that we have no seen in the area, no evidence of a early low temperature dolomite that can be seen as a seed for the complete dolomitization of the area. We have not seen this. We have no evidence of this dolomite. And talking about the reservoir quality, better in skeletal backstones, porosity and permeability increased by leaching of bioclast. Dolomites with higher degree of recrystallization also show better reservoir quality. Some dolomite bodies between limestones are also more porous and permeable. This is because we increase the lateral fluid flow because the original limestone facies are preventing the vertical fluid flow. In these dolomite bodies between these unreplaced limestones, we have also a better quality. And also, porosity and permeability enhanced by fracturing after dolomitization, of course. And I'm finishing the low reservoir quality of the field area of the dolostones today is because of 60% of the dolomite rock is a low porosity replacive texture. This is the replacive dolomite 1, which is low porosity, and also because we have a destruction, nearly complete destruction of the intercrystalline porosity by calcite cementation associated with uplift. And well, if we want to check for new cases for better reservoir quality characterization, these are expecting areas with no neogen extension. This should be checked to the west of the Meastart Basin. We are working on that now. And due to the occurrence of dolomite bodies above seismic and subseismic scale, the area can be used as an analog for the characterization of partially dolomitized carbonate reservoir, and thus it can be used for analog of hydrocarbon exploration and production. And that's all. I think I'm gonna
you are on time, Juan-D.
Okay. Yeah. Okay, perfect.
Thank you so much for a very nice presentation showing these excellent dolomite bodies, which are spectacular in view. I will show you some in the next presentation. We also have some similar kind of outcrop succession, so we'll try to compare them.
Okay, let's try.
Yeah. Yeah. Okay. Any question from the audience? If you have any question, so that we can ask from Juan-D.
Questions?
Yeah, one from Harun. Yes, Dr. Harun, floor is yours.
Thank you, Professor, for very nice presentation. In your model, you show mall and shales. Do they have any role in dolomitization? Do they enhance dolomitization? Or like if the limestone is argillaceous, it has a little bit of clay in it. Yeah. In your opinion, what does it have in dolomitization? Like, is there any catalyst or is there anything that you want to add?
Well, that's a very interesting question. When we were thinking about the origin of the magnesium for dolomitization, you have to think about a huge amount of fluid, because if we compare, and this is published in one paper by one of our collaborators, Enrique Gomez Rivas et al. 2014, I think. So he's evaluating the origin of the magnesium, and we assume that we can get some magnesium from the marls that they were showing, but the thickness of the units, of the marl units, and the amount of the dolomite we have, we can discard. Probably of course there are some local fluids coming from these marls and dolomitizing, but most of the dolomitization is not related to these marls or clays, because we have been checking that, and the volume of fluid, of magnesium-rich fluid, it's so high that we have to think something more. Well, it's something that is everywhere in the literature, no? Because when you think about the volume of dolomite you have to think in something with a lot of magnesium, and then you came to the seawater. So probably it's locally. Probably you can think about this origin in something very local, but if you think about the complete area, you have to go to seawater.
Thanks, Prof. Thank you for your time. Thank you.
Okay, thank you.
Yeah, Juan-D, one question regarding the Facies association and porosity distribution. What do you think that what kind of Facies you had good porosity values, and what were the tight ones?
You mean a time of dolomitization?
Yeah.
Yeah, but here it's also. I mean, this is interesting that I was showing images of facies like I don't know, palloidal grainstones that are completely cemented by early calcite cements, or oidal gravestones also completely cemented. So we have not completely control on that. I will say that, of course, the faces that has been replaced, or the units that has been replaced, they were probably the more porous and permeable phase at time of dolomitization, and I'm suggesting that these packstones and grainstones are these phases that has been more dolomitized, but there are some other control. So it's not only the positional control on dolomitization. There is something else. By the end, all of these controls interact with each other, and it's only not the positional. But I will say that at time of dolomitization, based on the analysis of the dolomite, the packstones and grainstones, mostly packstones and grainstones, palloidal packstones and grainstones, skeletal packstones and grainstones are the phases that has been dolomitized in a more intense manner.
Okay. Yeah. Rudy Shannon.
Yes,
yeah,
Juan Diego. Your case resembles quite well the Cantabrian Poncelagua situation.
Yeah.
But in the Cantabrian case, we see an evolution of an iron-rich dolomite first to a dolomite, and then the system seems not to have enough magnesium anymore, so it changed to a calcite system, and then the mineralization. Is this also something that you can see in your evolution?
Well, in our case, I would say that's something similar. Yeah, right. The question is that we were describing this dolomite cement, replaced dolomite 1 and replaced dolomite 2. All of them are more or less the same composition in terms of magnesium, calcium. All of them are more or less the same. But in general, in the setting we are describing, I will say that it's something similar. Yeah, something similar to what you were describing there in the Cantabrian Basin, which is more, I will say, still more spectacular, let's say, than this case study.
Okay, gracias.
Thank you, Rudy.
Okay, thank you, Juan, for a nice presentation and time that you spent on it. And we really enjoyed your presentation, and it was good to have some best outcrop, to see these best outcrops in this difficult time of COVID. So thank you so much again.
Okay, thank you. Fantastic.
Yeah. Okay, so it's time for me to show you